Hello and welcome back. In the previous two videos we studied motion in one dimension. So for example, in the very first video on kinematics we studied what happens if you have a car that's driving along a straight line with a constant acceleration or a constant deceleration. And in the previous video we studied, for example, what happens when you take a ball and you throw it vertically up in the air, or you launch a rocket vertically up in the air. And in this video, I want to start talking about what happens when you take, say, something like a ball and you throw it at an angle. So what happens if you take a ball and you throw it at an angle that's 30 degrees above the horizontal? How do we calculate what's going to happen in those cases? Now, the first thing I want to talk about, it's actually not on here, so I'll just open up a white screen here, is that when we have motion in two dimensions, we have to start using vectors. Okay? Now, we talked about these earlier. So, for example, the change in the position now has to have an x component and it'll have a y component. Same thing for velocity. We have an x component of the velocity, a y component of the velocity, and the same is true for the acceleration. Now, when we were studying motion in one dimension, we were actually using vectors. Now, we didn't write them out like this. We didn't think of them as vectors. We just treated one-dimensional velocity and acceleration as numbers, but they really were vectors. For example, when we look at vertical motion, we said that the up direction was positive, the down direction was negative. So this motion had direction, right? And we kept track of that direction with the sign of the displacement, the velocity, and acceleration. So for example, when we studied vertical motion, we said the acceleration was minus 9.8 meters per second squared, because the acceleration due to gravity points down, and we say that the down direction is the negative direction. The other thing that's very important to know about motion in two dimensions is that the equations which describe the x and y components of the motion are completely independent of each other. So here I have all the equations that we would use to describe the motion of an object in two dimensions. And you can see here this is split up into the x part on the left and the y component on the right. And the thing I want to point out about this is that the equations which describe the x component of the motion don't depend at all on what the y component's doing, right? So here we've got the x component of the velocity and delta x. We've got the acceleration in the x direction and the change in the x component of the velocity. So we've got all these delta x's, vx's, ax's, but nowhere here on the left does y make any appearance. Okay? Another thing to notice about this is that the equations we have here that describe the x component of the motion, they're the exact same equations that we've been dealing with in the previous two videos. We've got the equation for the velocity, the equation for the acceleration, right? This equation right here was one of the kinematic equations we derived in the first video on kinematics, and the same for this. This is the other kinematic equation we derived. And over here on the right, again, it's the exact same thing. We've got the exact same list of equations. We just got the y component of the velocity now, delta y, y component of acceleration, the difference in the y component of the velocities. It's just all these things now are referring to the y direction, and all these equations on the left refer to the x direction. So what this means is that when we're studying objects in two dimensions, you can literally break the problem up into two different problems. You've got a problem which studies motion in the x direction and a problem which studies motion in the y direction. And you can treat these two things exactly the same way that we did in the previous two videos. Okay, so we just go ahead and solve the x component and the y component exactly the same way that we did in the previous videos. Now, most of the time when we're studying constant acceleration, we're going to be studying free fall. Now, this is really, really useful because when you have free fall, this means that the x component of your acceleration will be 0 meters per second squared, and the y component will be 9.8, or minus 9.8. This is very, very useful because if we go back to the previous slide here, we can see that if my acceleration in the x direction is 0, then all of these equations down here go away. And the only equation we have that describes motion in the x direction is this equation right here. The velocity in the x direction is delta x over delta t. So this is really, really useful. When you have motion, it's free fall motion in two dimensions. This is the only equation we have for the x direction, and then the y direction is going to be just like it was in the previous video. We'll have these kinematic equations, the same kinematic equations we've had in the last two videos, and they will describe the motion in the y direction. We can use symmetry and all the other tricks we talked about in the previous video to discuss what's happening in the y direction. So I want to start off looking at a few examples, and I should warn you that these examples are a little bit tricky. Some of these are pretty complicated examples, but I want to go ahead and look at some of the more challenging problems so that hopefully when it's time to start working on the problem sets in class, they'll be a little bit easier. So this first example says, two airplanes are about to drop empty fuel cans. At the moment that the plane releases the fuel, the plane is traveling at a speed of 135 meters per second. Both of the planes are traveling at the same speed and the same height. The height is 2 kilometers. Now, even though the planes are traveling at the same speed, they have different velocities. Plane A is flying at an angle that's 15 degrees above the horizontal, and plane B is flying at an angle 15 degrees below the horizontal. Okay? So the initial velocities of our planes look something like this. So, again, when we have a problem like this, the first thing we want to do is we want to figure out what it is that we know and what it is that we are trying to figure out. Okay? So, looking at this, we can see that my initial velocity, or the magnitude of my initial velocity, is 135 meters per second. Okay? Now, the plane's flying at an initial height of 2 kilometers, but we're asked to find the final velocity when the fuel tanks hit the ground. So what this means is that delta y, the change in my y component of my motion, the vertical component, will be minus 2 kilometers. Okay? It'll be minus 2 kilometers because the object is starting out 2 kilometers high and it's going to fall to the ground. So the change in the y position will be negative 2 kilometers. It's going to go down 2 kilometers. Okay? And then we're also given these two angles. Now, whenever we have motion in 2 dimensions, the very first thing that you'll want to do is you'll want to separate this into x components and y components. And to do this, we have to decompose these initial velocity vectors. Okay? So here on the left, I didn't label this. This is plane A, and on the right we have plane B. And just looking at this now, the x component of my initial velocity, you can see, looking at this figure, this is adjacent to the angle that was given to us, this 15 degrees above the horizontal. So, remember, adjacent to the angle, that means we're going to use cosine. So the x component of my velocity is the initial speed times cosine of the angle 15 degrees. And if you plug this into a calculator, you see that this is 130.4 meters per second. The y component, the initial part of the y component, again, looking at this, we can see that this is opposite the angle, 15 degrees. So this means this is going to be equal to our initial speed times sine of 15 degrees. So plugging this into a calculator, we can see that this is going to be equal to 34.9 meters per second. And plane B, this is going to be very similar, right? Looking at this, we can see it's going to have the same x component. So the initial velocity in the x direction for plane B is 130.4 meters per second. And the y component, looking at this, the y component is initially pointing downwards. So it'll be negative 34.9 meters per second. Now remember that when we have motion in free fall motion in 2 dimensions, the x component of the velocity is never going to change because we don't have any acceleration in the x direction. Okay? So I already know what the x component of my final velocity is going to be. It's going to be 130.4 meters per second because there's no acceleration in the x direction. The velocity in the x direction doesn't change. So if my initial velocity in the x direction is 130.4 meters per second, my final velocity in the x direction is 130.4 meters per second. So all we have to do is find the final y component of my velocity, and then using that we can calculate the speed the fuel tank is traveling at when it hits the ground. So again, when we have 2-dimensional motion, we can just separate these things. So just looking at the y component, okay, so my known values, remember that the delta y, that was minus 2 kilometers, so that's 2 times 10 to the third meters my acceleration in the y direction is minus 9.8 meters per second squared. The initial velocity in the y direction is going to be 34.9 meters per second, plus or minus, depending which plane it is. And I know that, or what I'm trying to solve for, is the final value of the y component of the velocity. So this is what we're trying to solve for. Now actually, before I even start plugging numbers into any of this, I should step back and I should point out that we can really simplify this problem a lot using symmetry. Okay? So if we think about plane A and what it's doing, plane A, remember, this is the one that's moving upwards at an angle of 15 degrees. So if we think about the motion that'll occur for plane A, the fuel tank is going to travel up, it's going to reach some maximum height, and then it's going to come back down. And when the fuel tank returns to the initial height, that was 2 kilometers above the ground, okay, when the fuel tank returns back to that initial height that it was originally released from, okay, the y component of this velocity at this point is going to be minus the y component of the initial velocity, right? Remember that when we have free fall motion, that when the object is thrown upwards with an initial speed vy, when the object returns back to its initial height, it'll have the same speed, but it'll be traveling in the opposite direction. So over here, we'll have minus vy, okay? So if we think about this, what this means is that plane A is going to release a fuel tank, it's going to travel up, it's going to reach its maximum height, it's going to return back to its initial height, and when the fuel tank returns to its initial height, it's going to be traveling with the same velocity that the fuel tank that was released by plane B had, okay? This fuel tank right here is going to have the same x velocity as the fuel tank that was released by plane B, because the x velocities don't change, and the y velocity is going to be the same, okay? It's going to have the same magnitude in the opposite direction. So it's going to be exactly the same as the velocity of the fuel tank that was released by plane B. So what this means is that the speed of the fuel tank that's released by plane A is going to be the same as the speed of the fuel tank that's released by plane B when it hits the ground, okay? Because the fuel tank right here at this point is traveling at the same speed in the same direction at the same height from the ground as the fuel tank that was released by plane B, okay? So right away we can see that they're going to be the same. So all we have to do now is calculate the speed of the fuel tank that was released by one of the two planes, and we're done. So here I'm just going to pick, let's say, the fuel tank that was launched by plane A that was going vertically upwards. So looking at our knowns and our unknown values, we don't have anything about delta t in here. We were given delta y, we were given our initial velocity. We're trying to solve for the final velocity. So the kinematic equation we want to use is v final y squared is equal to the initial velocity squared plus 2a delta y. And notice that as I write this equation, I use the subscript y's here to indicate that we're talking about the y direction of the motion. So solving for the final velocity, all I got to do is take the square root. So we have v initial y squared plus 2ay delta y. This is 34.9 meters per second quantity squared plus 2 times minus 9.8 meters per second squared, and then minus 2,000 meters. Now notice that when we look at this equation here, this number on the right is going to be positive. We have minus 9.8 meters per second squared times minus 2,000 meters. Okay, so we have a negative number times a negative number. That gives us a positive number. Now, if we hadn't been very careful, say for example we said delta y was plus 2,000 meters, then this number on the right would be a negative number, and we would wind up trying to take the square root of a negative number, which obviously you can't do. So whenever you're using this equation, okay, you should be very careful that you're very careful about the signs of, the acceleration in delta y, okay? And one thing I want to say, I don't want to ever see anybody do this. Very commonly, if somebody makes a sign error and they have, say, minus 9.8 here and they have plus 2,000 here, and they say, oh, I'm taking the square root of a negative number, they'll just drop the negative sign. Okay? That's not going to give you the correct answer. Okay? If I had made a mistake here, and I had one of these were positive and one of these were negative, and then I just decided to drop the negative sign, I would get the wrong answer. Okay? Because what I really want to do is I want to add this number to this number over here. Okay? Because this number over here will be positive, so we'll be adding a positive number to a positive number. Okay? Now, if I take the difference between those two and then I just take the absolute value and square root it, I'm going to get something that's completely different. So I'll get the wrong answer if I'm not careful about my signs. But now if I plug this into my calculator, I see that this is going to be equal to 201 meters per second. So this is the final y component of my velocity. So this is how fast the fuel tank is traveling in the vertical direction when it hits the ground. So we know that the x component of the velocity, it doesn't change. We found before that that's 130.4 meters per second. So that's how fast the fuel tank is traveling in the horizontal direction. In the vertical direction, we found in the previous slide that that was 201 meters per second. So to find the speed that the fuel tank is traveling at when it hits the ground, we just take the magnitude of this. So remember, you take the x component and square it, plus the y component squared, and then you square root the whole thing. So we have 130.4 meters per second, quantity squared, plus 201 meters per second squared, and then you square root that. So if you take that and you plug that into a calculator, you see that this is equal to 239 meters per second. So that's how fast the fuel tank is traveling when it hits the ground. And that's the same for both planes. So let's go ahead and look at another example. This example says, the figure below shows an exaggerated view of a rifle that has been sighted for a target that's 91.4 meters away. If the muzzle speed of the bullet is 427 meters per second, what are the two possible angles, theta 1 and theta 2, this is this angle down here, between the barrel of the rifle and the horizontal, such that the bullet will travel up, come back down, and hit the target? So, again, the first thing we want to do is we want to look at this and see what are our knowns and unknown values. So the target is 91.4 meters away. So this is how far the thing's going to travel in the x direction. So we know that delta x is 91.4. Another thing that I don't really explicitly say up here, but we can see down in this figure that if the gun is sighted, what this means is that the bullet is going to come up and it's going to come back down and it's going to hit the target at the same height that the bullet was fired from. So what this means is that delta y will be 0 meters. Okay, so it's going to come up and then come back down, and when it returns to its initial height, that's where it hits the target. Now we're told that the initial speed, this is the magnitude of the initial velocity, is 427 meters per second. Okay? So again, the very first thing you want to do anytime we have something like this is we're going to need to decompose our velocities. Okay? So, right, the bullet is being fired at some angle theta above the horizontal. Okay? So we'll have some initial x component and we'll have some y component. Okay? So looking at this, we can see that the x component is adjacent to the angle. So we have v naught x is equal to the initial speed that I was traveling at times cosine of the angle theta. We don't know what this is, but we're going to try to solve for this angle theta. In the y direction, we have the same thing. It's going to be the initial speed times, and here we can see the y component is opposite the angle theta, so this will be sine theta. Okay, so this is the initial velocity of the object in its component form. Now, if we think about this, going back to this previous slide, okay, remember that in the x direction we don't have any acceleration. So what this is really saying is that the amount of time it takes for the bullet to travel 91.4 meters in the x direction needs to be equal to the amount of time it takes for the bullet to travel up and then come back down and return to its initial height. Okay? So this is really what we're looking at here. So, right, we can ask, okay, how long does it take for the bullet to travel 91.4 meters? Well, here's the x component of our velocity. So the only equation we have in the x direction, remember, is that Vx is equal to delta x over delta t. So solving for delta t, we see that delta t is equal to, so we multiply that over here and then divide the Vx, so we get it's going to be delta x over Vx. So this is the amount of time it takes for the bullet to travel 91.4 meters in the horizontal direction. Okay? And we said that this has to be equal to the amount of time it takes for the bullet to travel up and then return back to its initial height. So remember that, right, we have vertical motion here, we can use symmetry. So if an object travels up, reaches its maximum point, and then it comes back down, then delta v is going to be minus 2 times its initial velocity, right? Because, right, if we throw an object vertically up, it's got some initial velocity v0. When that object returns back to its initial height, it's going to be traveling downwards with the same speed but in the opposite direction. So the change in my velocity was twice my initial velocity, okay? So to figure out the amount of time it takes for this change in velocity to occur, we can just use the acceleration. So the acceleration in the y direction is going to be equal to delta v over delta t, and that's minus 2 v0 over delta t. Solving for delta t, we get that delta t is equal to minus 2 v0 over the acceleration in the y direction. Okay? Now the thing is it, right, this is the amount of time it takes for the bullet to travel up and then return to its initial height. In the previous slide, we calculated the amount of time it takes for the bullet to travel 91.4 meters. So these two things have to be equal, right? The amount of time it takes for the bullet to travel horizontally from this point to this has to be equal to the amount of time it takes for the bullet to come up and then return to its initial height. So we can set these two equations equal. So we have that delta x over Vx needs to equal 2 v0, this is the y component of v0, over delta y. Okay? So we have, let me write this down, this is delta x over Vx is equal to 2 v0 y over g, the acceleration due to gravity. So now what we need to do is we need to solve for the angle. So I need to rewrite this in terms of the speed the object is traveling at and the angle, right? Right now I have the x component of my velocity and the y component of my velocity. So now I need to rewrite this in terms of a magnitude and direction. So here we have delta x is divided by, this is the initial speed times cosine of the angle. Here, remember this is the initial speed times sine of the angle. So now I'm trying to solve for the angle theta, so let me move all these sines and cosines to one side. So if I, say, multiply this cosine over here, I get 2 v0 sine of theta cosine theta over g is equal to delta x over v0. Or, again, just isolating the sines and cosines, I could write this as 2 sine theta cosine theta is equal to multiplying the g dividing by v0. This is going to be g delta x divided by v0 squared. This is the initial velocity squared here. Okay? Now, this, as I said at the beginning, these problems are pretty tricky. And looking at this, you might say, well, how am I going to solve for the angle theta? I've got sine and cosine here. This is not easy to do. But it turns out, and I wouldn't expect anybody in here to actually realize this, but 2 sine theta cosine theta, that's actually a trig identity. So that is going to be equal to sine of 2 theta. So now we have sine of 2 theta is equal to g delta x over the initial speed squared. So now we can pretty easily see that we can solve this. So if I take arc sine, then I get 2 theta is equal to the arc sine of g delta x over v naught squared. So theta is 1/2 arc sine of g delta x over v naught squared. So if I plug all this into a calculator, if I plug in g is, minus 9.8, and I plug in delta x is that 91.4 meters, I think, and my initial speed, whatever that was, I don't remember. But if I plug all these values into a calculator, I'll see that this is equal to 0.141 degrees. Now at the very beginning of this, I said that there were two angles, theta 1 and theta 2, and I said one was way too large, you would never actually use it. So now I want to think about what this other angle is, because this is what I get when I type into my calculator, but I just get one answer from my calculator. So let's think about this just a little bit more. Oh, I need to get a blank sheet here. So let's think about sine for a minute, right? If this is an angle theta, sine, remember, is this, it's the opposite, this part right here, this is delta y, divided by the hypotenuse, okay? So if this is coordinates, this is, say, x, and this is y here, okay? Sine will be positive in this quadrant and in this quadrant, and it's going to be negative in these two quadrants, right? Because over here, right, my y value, which is opposite the angle theta, is positive, and over here, right, my y value over here is also going to be positive, okay, because I'm above the x-axis, okay? So one of these angles that we found, it was actually, if we think about this, right, so half of the arc sine was this, so the angle arc sine is, 0.282 degrees, okay? Oh no, I just got rid of my screen, I didn't mean to do that. So we found one angle up here, okay? The other angle that works is this angle over here. And this angle over here, we can see this is 180 degrees minus this angle theta, okay? So the other place this is going to work is at 1/2 times 180 degrees minus arc sine of g delta x over v naught squared, okay? Because this is the other angle. It's at 180 degrees minus that arc sine. So if I plug this into a calculator, I'll see that this one is equal to 89.86 degrees. So that's where the other angle comes from. It's a little bit tricky. So let's go ahead and look at just one last example for 2D motion. So this example says, a small can is hanging from the ceiling and a rifle is aimed directly at the can. The instant the gun is fired, the can is released. Ignoring air resistance, show that the bullet will always hit the can regardless of how fast the bullet's traveling. Okay, so this is like a classic problem. I'm taking a gun and I'm pointing it straight at the can, and the instant the gun is fired, the bullet's dropped, and no matter what, the bullet's always going to hit the can. So how do we show that that's going to happen? Okay, well, again, just like always, we need to decompose my initial velocity, right? I've got to break this into an x component and a y component so I can solve the two separately. So the x component of my initial velocity, it's just like all the other ones, it's adjacent to the angle theta, so it's going to be v naught cosine of theta. And the y component is going to be v naught sine theta. Now the other thing that's a little bit tricky about this problem, if we look at this, we can actually see that this angle theta is related to the distance between the gun and the can and the x direction and the y direction, right? So we can see we get this little triangle here, right? This is how the gun was pointed, okay? And this thing down here, right, this is how far the bullet's going to travel in the x direction. And up here, right, this is how high the can was initially. So we can see that sine of theta, right, this is opposite over the hypotenuse. And I'm just going to call this hypotenuse d. We'll see this will actually drop out of the problem, so it doesn't matter. We can see that this is y naught can over d, right? This is the initial height of the can divided by this number d. And cosine of theta, that's adjacent over hypotenuse. This is the distance that the bullet travels in the x direction divided by d. Okay? So, what we need to do to show that this is going to happen is that we need to show that when the bullet travels in the x direction, some distance, delta x bullet, that the height of the bullet at this point is equal to the height of the can. Okay? So, during the amount of time it takes for the bullet to travel a horizontal distance of this x bullet, the height of the can is equal to the height of the bullet. So the first thing we need to do is figure out how long it takes for the bullet to travel this distance x in the x direction, this delta x. Okay, now remember that for free fall motion, the x direction is really easy. We have that vx is equal to delta x over delta t. Okay, so the amount of time it takes, delta t, is just going to be equal to delta x over vx. And that is delta x over v naught cosine of theta. Okay, so that's the amount of time it takes for the bullet to travel in the x direction. Okay, so what I need to do is show that the height of the can is equal to the height of the bullet. So to do this, I have to calculate the height of the bullet and the height of the can at this time. Okay, so let's see, which one do we want to pick first? I guess we'll pick the bullet first. Okay, so the bullet, right, it's traveling upwards with some initial velocity in the y direction that's given by this v naught sine of theta. Okay, and I guess it's just free fall motion. Okay, so I'm traveling upwards with some speed, v naught sine theta. I'm going to travel up, right, and I'm constantly accelerating down. So my motion in the y direction is given by this delta y equals minus 1/2 g delta t squared plus v naught in the y direction times delta t. Right. So let's see. Here we have minus 1/2 g. And over here we have delta x divided by v naught cosine of theta. Actually, before let me simplify this a little bit further. Right? So I can rewrite this. Cosine of theta is equal to delta x over d. So cosine of theta, this is going to equal delta x divided by v naught delta x over d. And when we do this, we can see the delta x's cancel, and this is just going to be equal to d over v naught. So let me use that in here. So delta t is equal to this number d divided by v naught squared. Actually, before I continue, I should point out this equation right here should actually make a lot of sense. This delta y is equal to d over v naught. Okay? Because remember, I said at the beginning that the motion in the x direction and the y direction completely decouple. Okay? So, right, if there was no acceleration in the y direction, if there was no gravity, the amount of time it would take for the bullet to travel this far in the x direction is the amount of time it would take for the bullet to travel a distance d moving at a speed v naught. Right? If there's no acceleration, right, the bullet would just travel in a straight line. It wouldn't take this blue path, okay? And the amount of time it takes for it to travel in the x direction, this distance right here, is just the amount of time it takes for it to travel this total distance here. Right? So we can easily see that delta t would just be d divided by v naught. Right? And now if I add acceleration in the y direction, well, it doesn't change that, right? Because my x direction doesn't depend on what's going on in the y direction. So if it takes an amount of time, d divided by v naught for the bullet to travel this far in the x direction with the acceleration, and with the gravity turned off, it'll be the same when I turn gravity on, right? So it just doesn't depend on what's going on in that vertical direction. It'll be the same. So this equation right here is this very neat idea, right? It just comes from, it's the same thing as if gravity was turned off. That's the amount of time it takes for the bullet to travel in the x direction, no matter what, because it doesn't depend on what's going on in the y direction. Okay? So I can plug this in to this equation here, which is describing the motion of the bullet, right? So we've got this plus v naught in the y direction times d over v naught. And finally, if I want to, I can simplify this a little bit further. Right? V naught in the y direction, that's v naught sine of theta, and sine of theta is the height of the can divided by d. Okay? So this is, let's see, this is v naught times sine of theta, and sine of theta is the height of the can divided by d. And immediately we can see a whole bunch of things are going to simplify here. V naught is going to cancel, and D is going to cancel. So this whole thing over here is just going to be equal to minus 1/2 G. Now when I write at the bottom of the screen here, it doesn't like that. So minus 1/2 G D over V naught squared plus the initial height of the can. And some of you may already be able to see that this is going to be the height of the can after it's fallen this amount of time, okay? But let's just go ahead and show that on the next slide here. So the can's starting out at some initial height, Vy can, right? So the can's starting out and it's going to drop down due to the acceleration due to gravity. So what is the height of the can? Well, the height of the can is going to be equal to its initial height minus the distance that it's fallen, 1/2 G delta T squared. And delta T is equal to, we saw this in the previous slide, that's the D over V naught. So plugging D over V naught into this, we get that the height of the can will be the initial height of the can minus 1/2 G D over V naught squared. Notice that this here, this is the height of the can after the bullet's traveled in the x direction, a distance delta x, is equal to this height right here. This is the height of the bullet after the bullet's traveled in a distance delta x. These two things are the same, okay? So the height of the bullet is equal to the height of the can. So the bullet will always hit the can when the can is released at the same moment that the bullet is fired. So that's about it for the two-dimensional kinematics. Like I said, these examples are pretty challenging. That last one especially is a particularly challenging problem. The practice problems will be much easier than this. And in the next lecture, in the next video, we'll talk about graphical analysis. So when we look at the position of an object versus time, a graph of the velocity of the object versus time, how we can look at those graphs and extract information from those graphs and figure out what's going on.